In this video, we're going to start Chapter 5 of the statics textbook. Chapter 5 is on equilibrium of a rigid body. Now, Chapter 3 was equilibrium of a particle, and if you've been going through this course from the beginning, you should have a sense for what the difference is between the equilibrium of a particle and the equilibrium of a rigid body, but we'll talk about this again in a few minutes. So we started out in Chapter 1. Chapter 1 was like a typical introductory chapter for a science book or an engineering book. It's not so much about that actual subject. It's like, we talk about units, the SI units, English units, significant figures, rounding, things like that. We did talk about the idea of what is mechanics in general. So again, mechanics is the subject where you're studying bodies, solid, liquid, or gas bodies that have forces applied on the body, and you're studying the effects of those forces on the body. Now, thinking about solid bodies, in the majority of cases for engineering mechanics, the solid bodies have negligible amount of deformation when the forces are applied to those bodies. So we make the simplifying assumption that the body actually doesn't deform when the load is applied to it. So in other words, here's this big steel pipe or, whatever. I'm not sure if that's a pipe, but it's not like it's sagging like this, right? So the load application is changing. Even if you have a beam, like a cross beam in a building, it's not like those beams are deforming in any noticeable amount relative to the loads. So we assume that they're rigid, that they don't deform, so that we don't have to say, like here, the forces from these wires are acting up. We don't have to say, well, before the load is applied, the forces are acting in this direction, and then after the load is applied, the forces change directions to like this direction. We don't have to look at it that way. That would overcomplicate the problem, and it's not necessary. Okay, then we learned about force vectors. We learned about vectors in general, just vector operations, and also learned about specifically force vectors and everything there is to know about force vectors, projecting force vectors onto different directions, creating a force vector, things like that. But forces also cause rotations. You have to consider, for force systems, it's not just forces, but also the tendency of rotation that they cause. So we learned about the concept of a moment in Chapter 4, how to calculate moments, how to project moments onto axes and different directions, special types of moments like couple moments. We also learned how to work with distributed loads. So the majority of the time we're considering the concentrated force simplifying assumption. So we just put the force on something with an arrow like that. And when we do that, we're assuming that the area over which the force is applied, because unless you're dealing with a body force like gravity or electricity or magnetism, it's going to be a contact force. There's always going to be some area of contact. If that area of contact is small relative to the entire body, you can just put a point force like this. But if the area happens to be, it's not negligibly small, you have to use a distributed load. And so we learned about how you work. How do we work with distributed loads? How can we simplify them so that we can analyze the force system like we're gonna see here in this upcoming chapter? Okay, and again, I'll mention what Chapter 3 was about in a second. Okay, so now that we understand how to represent forces and represent moments, we want to apply the actual engineering static analysis on something. So that's really what this course is all about. That's what statics is all about. You're applying the equations of equilibrium, you're applying Newton's second law to a body that happens to be not accelerating, so it's in equilibrium. In most cases that it's not moving, but it could also technically be at constant velocity, but for the majority of the cases it's going to be not moving. You apply Newton's second law to some body, some solid body. We're talking about solid bodies in this course. And by doing that, it allows you to solve for all of the unknown forces on the body. There's going to be some known forces. You're going to know something about the problem, and then using Newton's second law, that's the equations of equilibrium, you can solve for all of the forces. You already know the known forces, but so you solve for all of the unknown forces. Now you know all of the forces that are acting on a body. And that's it. And that's what statics is all about. That's it. You want to know the unknown forces at a connection, so you can make sure that connection is large enough to hold the weight, for example. Okay, now the first step for doing any analysis in mechanics, and really in all of mechanics, but let's focus here on rigid body mechanics. So we're thinking about solids right now. This also applies to statics as well as dynamics. But the first step is drawing an accurate free body diagram of a body. You're trying to analyze a body to solve for all of the unknown forces on it. That's the goal. To do this, to solve for all these forces, the first step is to draw an accurate free body diagram. And just before this video, I made a 2-hour-long video on free body diagrams. That's one of the longest videos, if not the longest video that's on this channel, because it's so important. I go through it in detail. It's a really good video. I took my time on it. You'll get your money's worth or your time's worth watching that video. And so try and go watch that video. You don't have to watch it before watching this, but either before or after you watch this video, make sure you check out that full-length free body diagram video. I'll post a link to it in the description. Okay, but with that, I'm going to assume that you have a general understanding for what a free body diagram is. I'm not going to spend too much time on free body diagrams here in this video. Okay, so again, you picked out a body that you want to solve for all of the forces that are acting on it. It could be this entire submarine, or just to give an example, here's a bobcat. Let's assume it's like in full operation, right? It's got like like a big load on it. You can think about the designers will do a bunch of free body diagrams. They'll pick out all kinds of components. A free body diagram can be on just a single component or an assembly of connected components. They're connected rigidly with, like bolts. Even with the bolted connection, they don't deform, at least in the direction of the load. So again, the designers will do a bunch of free body diagrams. Maybe just this one big component here. Maybe this component connected with this component as well. They'll do all kinds of free body diagrams, solve for all the forces and all the connections. All the forces even within the connections, and also within like the actual members themselves, like the internal forces within this. You can think of this like a beam here. Okay, so now let's assume you've got your accurately drawn free body diagram for some component or some system of connected components. With that, that's where they're starting here. They're looking at this as this is as general of a free body diagram as it gets. This is a completely random 3D shape with forces in random directions as well as couple moments. And we talked about in the free body diagram video, if you're thinking about just a general scenario in nature, if you're driving down the road and you look at something and you're thinking about what are the forces acting on that something. Technically, the only thing that exists in nature are forces. There's no such thing as moments or even couple moments. That's something that humans, engineers, scientists made up. Moments is a concept that we made up. Really, there's only forces. Because like forces are cause moments, right? Like a couple moment, this couple moment is in reality, it's some force pair that's equal in opposite directions and separated. That's what a couple moment is, right? So really, anything you see in nature, any body that you think about, what are the forces acting on it? It's just forces. But in engineering, in this course, the way we're going to think about it is in a general body, in just complete general, is going to be potentially have forces and couple moments acting on it. Nothing else. That's it. You might say, what about moments about points? No, a general free body diagram that you're going to be applying Newton's second law to in statics or dynamics has no moments about points. It's couple moments and forces. That's it. And you might say, well, where does this come from? Remember, in the previous chapter, you could take a general force system, just the most general force system, which is like something you'd find in nature. It's just forces acting on a body, and you could simplify that down to a force and a couple moment at a point. It's all forces and couple moments. Moments about points is just an analysis technique. It's something you can analyze about a body. Like I can say, okay, if this is like some sort of wrench setup, and it's very important, if you're designing a motor or something to where it's for the functioning of that component or that machine or whatever, the moment generated about an axis or about a point is very important. Well, I could always look at this force system and say, okay, what's the moment about this point? Then I change up the parameters, I change up the force system, and I say, okay, what's the moment about that point? And I design it to where it creates a moment about this point that I want, right? I'm trying to design the whole system to create a net moment about this point or about this axis. A net tendency of the forces, of all of the forces to cause rotation about that point or about that axis. That makes perfect sense. But when you're just thinking about the free body diagram, applying Newton's second law, the equations of equilibrium, or just Newton's second law for dynamics, it's not an equilibrium. It's just forces and couple moments. A couple moment, remember, is a free vector. A moment about a point is fixed at that point. A moment about an axis is fixed on that axis. A couple moment is a free vector. If you want to move a force, if you want to simplify a force system, move a force to a point, you get a resultant force at that point and a couple moment at that point, not a moment about that point. If I want to move this force here, I move the force here, calculate the moment of this force about this point, and put that moment at the point, but it's a couple moment. I can technically put that couple moment, it's a free vector. I can put it wherever I want, but I put it at that point just because that's the standard convention. It makes the most sense. But I can technically put it wherever I want. Okay. So now we've got our free body diagram accurately drawn with forces and couple moments. So in this section, we will develop both the necessary and sufficient conditions for the equilibrium of the rigid body in figure 5.1a. So we're assuming it's a rigid body, and that's a perfectly good assumption for if you're dealing with a solid. Typically, the solid doesn't deform when the loads are applied to it. As shown, this body is subjected to an external force and couple moment system that is the result of the effects of gravitational, electric, magnetic, or contact forces caused by adjacent bodies. The internal forces caused by interactions between particles within the body are not shown in this figure because these forces occur in equal but opposite collinear pairs and hence will cancel out, a consequence of Newton's third law, right? So we do not put internal forces on free body diagrams. We talked about this in the full-length video. Using the methods of the previous chapter, the force and couple moment system acting on a body can be reduced to an equivalent resultant force and resultant couple moment at any arbitrary point O on or off the body, right? Any general force couple moment system, you can reduce that to a force and couple moment at a point, and it can be on or off the body, that point. If this resultant force and couple moment are both equal to 0, then the body is said to be in equilibrium. Mathematically, the equilibrium of a body is expressed as the resultant force is equal to 0. And how do you calculate that resultant force? You just do a vector sum on all the forces, right? That's what we learned. And how do you calculate that resultant couple moment? You sum the moments about that point. You sum moments about the point, and then the resultant moment you get is a couple moment. That's how you move. That's how you simplify a force system and also couple moment system, external force and external couple moment system down to just a single force and couple moment at a point. And what it's saying is a body is in equilibrium if that resultant force is equal to 0 and that resultant couple moment is equal to 0. That's what the equilibrium of a rigid body is. This is in general 3D. This is the general idea of what equilibrium of a rigid body is. I'm going to say it again. We know from the previous chapter, you have a general force and couple moment system acting on a body, and we're talking about a rigid body. A general force and couple moment system, that is the most general case you'll see in nature. Nothing else. A force and couple moment system. We know that we can reduce, no matter how complex and three-dimensional it is, we can reduce that system down to a single force and single couple moment at a point. If that resultant force, which we know from the previous chapter, we get that resultant force by doing a vector sum on all of the forces. If that resultant force is equal to 0 and that resultant couple moment, which we know we get by summing the moments of all the forces about that point, if that resultant couple moment is equal to 0, then the body is said to be in equilibrium. Okay, the first of these equations states that the sum of the forces acting on the body is equal to 0. The second equation states that the sum of the moments of all the forces in the system about point O added to all the couple moments is equal to 0. Yeah, that's right. So to get the net resultant couple moment, you sum the moments of all the forces about that point. You'll get a vector sum there, but you also, if there's any external couple moments, you do a vector sum on that as well. You just kind of move those to point O as well. Okay, these two equations are not only necessary for equilibrium, they are also sufficient. So a quick aside here, this idea of necessary and sufficient conditions, that's like if here's an example. I'm looking for the conditions to create a rectangle. Okay? I could have a square, or I could have a quadrilateral. A quadrilateral is a necessary condition to have a rectangle. If I don't have a quadrilateral, I cannot have a rectangle. A square is a sufficient condition to have a rectangle, because to be a rectangle, it doesn't have to be a square. So this is sufficient, right? A square is sufficient, but it's not necessary. It doesn't have to be a square to be a rectangle. So this is just sufficient. Having a square to have a rectangle is sufficient, but having a quadrilateral to have a rectangle is necessary. I cannot have a rectangle unless I have a quadrilateral. All right. Okay, so to show that these two equations are necessary for equilibrium and also sufficient, and to kind of explain to you what they're saying, here we just did the transformation. We transformed the force system to a force and couple moment at a point. That's all we did. And they're saying that, so this is necessary. That's what this definition, that's based on this definition. If you take a force system and you simplify it to a force, resultant force and couple moment at a point, just any point, then that means that the body is in equilibrium. That's necessary. I mean, that's the definition, right? By definition, that's necessary. But they want to show that this is sufficient in the sense that you could argue, well, don't we need to perhaps then redo the simplification about this point and make sure that the resultant force is zero, and then also this point? Why is this necessary as well as sufficient? And so what they do is they say, let's take this force couple moment system and move it to another point. This is an equivalent system to this. So we can, instead of restarting, we can just go ahead and move this force couple moment system to another point, point A. All right, so what do? We do a vector sum of all the forces and move that force vector to point A. Well, there's just one force, so just move the force vector here. Then we sum we find the moment of all the forces, this one force about point A, and also move the couple moments. So we move this couple moment to point A and then find the moment of this force about point A and sum those two vectors, which is looking at the moments. Some of the moments about point A is R cross FR plus that MR 0. And this needs to be equal to 0. The sum of the moments need to be equal to 0. And it says since R is definitely not 0, we're definitely moving off the main point, the first point. This equation is satisfied only if these equations are satisfied, right? So since R can't be 0, the only way for this to be satisfied is that this has to be 0 and this has to be 0. Otherwise, there's ambiguity, because, like, all right, we've assumed that this is true. Okay, this is the necessary condition. We're trying to show that it's sufficient. So we've assumed that this is true. Let's say R could be equal to 0. Let's say the constraints for this were that R could be 0. Well, if that's the case, then this equation could be satisfied, and you don't have FR equal to 0. You could have a non-zero FR, and this equation is satisfied. But since R can't be 0, if this is the case, then there's no way that we can move to another point and get a non-zero result for the resultant force or the sum of the moments about that other point. So what this is saying is that for a rigid body to be in equilibrium, to show that a rigid body is in equilibrium, all you have to do is, if you take the full force system on the free body diagram, the accurately draw free body diagram, the force and couple moment system, if there are couple moments, you simplify that system down to a resultant force and resultant couple moment about any point you want. It doesn't matter what the point is. And if the resultant force at that point is equal to 0 and the resultant couple moment is equal to 0, then that body is in equilibrium, no matter what point you choose. That's what static equilibrium means. Okay, now here they just talk about how we're dealing with rigid bodies, and go watch the full-length free body diagram video. I talk about how it's not like if you're dealing with a body that's not rigid, then all of a sudden you can't apply the equations of equilibrium, or you can't apply Newton's second law anymore, or the equations of equilibrium. That's not what this is saying. It sounds like it's what it's saying, but you don't look at it that way. Let me say that again. This doesn't mean that if you don't have a rigid body, so if the body is deforming a good bit once the loads are applied, that all of a sudden you can't use Newton's second law. You can't apply the equations of equilibrium at all. However, as far as this course is concerned, as far as this textbook is concerned, every scenario we're considering is a rigid body scenario. Because if it wasn't a rigid body, yes, you could still apply the analysis that we do in this course, but it's more complicated, though. You have to consider what happens to the forces when the body deforms, and so you can't make any definitive statements like this textbook is going to make if the body isn't rigid. So everything we're talking about in this course, in this textbook, we're talking about rigid bodies. If it's not a rigid body, then while you can still apply this type of analysis, it would be a different circumstance. And I give more specifics on this in the full-length video. Okay. Equilibrium in 2 dimensions. We're going to start with 2 dimensions. So we're going to have a free body diagram that's a planar free body diagram. Then because of that, the equilibrium analysis that we do is going to be in 2 dimensions. So now we're talking about a free body diagram, a planar free body diagram. It's talking about what a free body diagram is, why it's so important. Go check out that full-length video. I go into detail on what is required to have a planar free body diagram problem, and I talk all about free body diagrams. I go into all this kind of stuff. Okay, support reactions. So there's 2 types of forces in the universe. Only 2 types. You can categorize every force that possibly exists in the universe into 2 types, into 2 categories: body forces and surface forces. Surface or contact forces. That's the same thing. A body force is going to be gravity, electricity, magnetism. That's it. Now, that's assuming that you have a non-accelerating reference frame, which is, unless you get into more advanced like physics studies, in general engineering, that's all you're dealing with. And for accelerating frames of reference, there's other body forces that can come into play, like centrifugal, like fictitious centrifugal body forces, things like that. But that would be a topic for a faraway subject down the road. We're thinking about, we have a fixed reference frame, a non-accelerating, even non-moving reference frame. We're observing the situation from a still position. If that's the case, the only body forces are gravity, electricity, magnetism. And we talked about, in a previous video, we talked about how body forces, like gravity, for example, they act equally in the same magnitude and direction on, it's a safe assumption to assume that the body force acts equally in magnitude and direction on all particles of the body. So you can put that body force at the center of gravity, or like the electrical type center, like a centroid type position. It might be the center, like the actual geometrical center of the body, unless it's like the mass is not uniform, then it'll be like the center of mass instead of the actual centroid position of the body. Similar idea with electricity and magnetism. If it's not a body force, it's going to be a surface force or a contact force, meaning the force on the body is coming from contact with something else. There must be contact. Think about that concept. It's really helpful. If it's not electricity, gravity, or magnetism, then if there's no contact, there is no force. There's no force that you have ever seen in your life outside of you jump in the air and the earth like magically pulls you back, or like a magnetic force or an electrical force. There's no force that you have ever seen that there wasn't contact that was causing the force. Okay? Now, when you think about contact forces, you can separate contact forces into 2 types, 2 categories. It's either going to be some sort of an external force, meaning like if you have a machine, it's something that's coming from the environment or something that's part of that machine's operation. So a crane lifting something, the force from something it's lifting, it's part of its operating, it's part of how it operates. That's an external force. A cross beam in a building, the force from the people, the furniture, the weight on the beam, that's an external force. If it's not an external force, then it's going to be a support, which is called a reaction force. So it's like it says, it's a support. Like in the machine, the crane, the bolt, like something that's the force from the bolt holding the big beam, keeping it from, falling, from rotating, keeping it still. The cross beam in the building, the actual, the what's supporting it at the ends. Those are contact forces, contact from the bolts on the beam, let's say. Okay, so here, this section wants to focus on the support reactions. And so you're doing a free body diagram. You're trying to make a free body diagram of either a component by itself or a system of connected components. And you're trying to represent all the forces on that body. And the way you do that is with a mental exercise that it talks about here. It's saying, so you've removed a body or a system of connected bodies from its supports, and you want to now add appropriate forces to the free body diagram to be representative of that support, accurately representative of that support. How do you do that? Well, you use this mental exercise. You say, if the support prevents the translation of a body in a given direction, then a force is developed on the body in that direction. If rotation is prevented, a couple moment is exerted on the body. Okay, so looking here, this roller, this doesn't prevent movement in this direction. It doesn't prevent movement in this direction either. It only prevents movement in this direction. So there's a force in that direction, and there's going to be no component of this force. This force can't be at an angle because it can't resist motion in this direction. And it also, if this beam wants to rotate, the roller can't prevent that, right? If this beam wants to do anything, even if there's just, let's say there's some large loads here, so the beam isn't like actually spinning, but the beam can deform down, and this can change the angle of this face. This face, if it's unloaded, is at a straight up and down. The angle of that face can change based on the loads here, right? So it's not stopping any rotation, this roller. So that's the force you put for the free body diagram that's representative of this support. So that's the idea of a roller. What about a pin connection? What does a pin connection prevent? Well, here the beam can't move in this direction or this direction, but it doesn't prevent any rotation. That's the idea of a pin connection. A pin connection prevents translation in any direction, but it doesn't prevent rotation. That's the idea of a pin. So you can put a force at an angle or just an Fy, Fx. These are the same. Typically you do this, but you could do, there's two unknowns here, an F and an angle, or there's two unknowns here, an Fx and an Fy. But it does not prevent any rotation, right? Think about if you had some big beam loads, if it was fixed on the other end somehow, and as a result of those beam loads, the beam wanted to deflect. This face here starts off before any load, it's straight up and down. After loading, that face can go at an angle, so it can rotate. As opposed to here at a fixed support, this prevents, obviously, it can't translate in the X or Y, but also that face can't rotate, right? This face starts off straight up and down. You put some loads here. The beam, at least if you zoomed in really close, the beam wants to deflect. I mean, that's what it's technically doing. If you zoomed in really close, it's a rigid body, but if you zoomed in really close, it's definitely deflecting. But here, this can't deflect with it. This support here, that face can't deflect with it. This can't turn in at an angle. It can't rotate. So you put a couple moment in addition to the Fx and Fy, the two forces. It prevents translation. A fixed support prevents translation, and it prevents rotation. Now, keep in mind that this is two dimensions. In a separate video, we'll take a look at this idea of support reactions in 3 dimensions. But the concepts are going to be the same. A pin is going to prevent translation in all directions in 3D. A roller is going to prevent translation only in certain directions, but not in other directions, even in 3D. And a fixed support is going to prevent translation in all directions, so you'll have Fx, Fy, Fz, and rotation, so you'll have Mx, My, Mz. Here you have Fx, Fy, Fz. Here, Mx, My, Mz, Fx, Fy, Fz. And here only like Fx or Fy and not Fz or something like that. You'll have at least one degree of freedom that the component is not constrained in. Now, you might be saying, well, wait, this pin can prevent rotation here. This beam can't rotate in this direction or this direction. Similar idea here. If you tried to rotate the beam into or out of the page, that roller would, you would, as long as the roller is at least the thickness of the beam, it would stop rotation. The way you think about that is, so yes, technically you're right. If you walked up to this beam and you were a strong person, you tried to rotate the beam by hand, it's not going to move in that direction. But the idea is, when you think about the loads, the magnitude of the loads that the pin in the actual directions, in these directions that this pin is stopping movement from, the loads in these pins. If there was any kind of rotating motion in this direction that was even in the ballpark of these forces, it would break that connection. That connection is not designed, that pin connection is not designed to stop any significant rotations or even translations in this direction, right? You might say, well, it can prevent translation. This kind of connection is not designed for that. The whole thing would fail. That's why it's a 2D problem. That's why it's a planar problem, because even though there's technically forces that are into or out of the page coming here. Technically, there might be forces into or out of the page. I mean, technically, there always will be. There could be small gusts of wind into or out of the page. Those forces are negligible compared to the forces that are in the plane. Come back here. If they aren't negligible, then you need another connection. This connection is wrong. You need a 3D connection. Okay, now also notice that if you want to represent a force from a support piece, a reaction force that's preventing rotation, you put a couple moment. There's nothing about moments about points. It's always going to be forces and couple moments that are acting on bodies. And one way you can think about this that'll help you if you're having trouble wrapping your mind around that idea. Let's say you were gonna put an external force on a beam or whatever. You're trying to represent an external force from whatever it is, wind, or you can even think about, let's say you were the Hulk and you're going to apply a force as you can apply a beam force to a beam. Think about what is all of the possible ways you can apply a force. You might say, yeah, you can apply a moment about a point. So if this is a beam, let's say it's fixed over here and pinned over here. If you're the Hulk, you apply a force. It'd be a distributed load, some sort of distributed load, maybe with both of your hands. I don't know. You're applying a moment about a point. But no, that's what I'm saying is we talked about in the Newton's laws video how, if you're in space and you push on a ship, that then Newton's third law, that equal and opposite force, will be acted on you. And then so if you pushed on a ship purely with no rotation, then you would move in the opposite direction based on that force you applied. So yeah, there's a moment about this point, but like if as the Hulk, there's no rotation here. You're just if you're in empty space, you're just gonna go back and with a linear motion, and your body won't be rotating. Right? We're strictly talking about the applied force. There is a moment about this point, but you didn't apply a moment here. There's no moment here. But let's say, okay, so you applied a pure non-twisting force, but let's say you kind of, you decided to push on the beam a little bit on one end and then kind of pull it on the other end. You also, in addition to some linear force, you tried to also rotate the beam a little bit. Well, what you're going to have is, if you separate out the components of that, you're going to have some of that force is going to be just a linear force, pure linear, but then there's going to be some portions of that where you've got equal and opposite force that's separated by a distance. It's a twisting, a couple moment, right? You can separate that out into some of this force is like this, and then some of this force is like this, and you can turn that into a couple moment. So now after you're the Hulk, you applied that, you're going to go away from the beam in empty space. and you're going to be moving in a linear direction, and also your body's going to be spinning. But again, the only thing you could possibly apply is a linear force or a couple moment. That's it. There's no moments about points when you're thinking about free body diagrams. There's no moments about points. It's either force or couple moment. Technically, it's only just force, right? Because even this couple moment is really just two forces. But we think about it as just forces and couple moments. If any component of a net force applied by something is this equal and opposite pair of force separated by a distance, you just turn that into a couple moment. So all you're left with is the translational portion of the force and the spinning portion of the force. Here, it shows a table of different types of support reactions. Again, this is just two-dimensional. We're going to see another table like this in an upcoming video for 3 dimensions. But let's take a look here. So here's a cable, and we know that for something like a cable, the force in the cable is in the line of action of the cable. So you have a force at this angle theta, and perhaps that angle theta is variable depending on the setup. Maybe this angle is fixed and you know the angle. Maybe this angle can vary, but you'll always know the line of action of the force is in the direction of the cable. A weightless link, really exact same idea as the cable. Here, a roller. We're imagining this is a pin here, but you're imagining that if you do the free body diagram, you leave this connection here and just take all this out. There's no friction, so the force there can be, meaning since there's no friction, there can be no component of force parallel to the surface. Now you might be saying, what about friction in the wheels? Same idea as just talked about. The force, the resistance from the friction in the wheels would be negligible compared to the actual magnitude of this force. But if there was actually enough friction in the wheels to have any sufficient magnitude, then you need to change out the wheels. All right, this roller, if you're assuming no friction, so it would just be normal. The force would always be normal to both the surface of the roller and the contact surface. Well, this contact surface doesn't change, so this force is perpendicular to the contact surface, and you know the angle of the surface, so you know the angle of the force. Same idea, but there's no roller, but it doesn't matter. The force, since it's a smooth contact, the force is always going to be perpendicular to the surface, the contact surface. Same idea here. There's no friction. If there was friction, like here, if there was friction, then there would be a component of the force that's perpendicular to the surface. That's the idea of friction. But they're saying smooth, and if it's a roller or a rocker, then you don't have to assume smooth surface. There's no way like a roller is going to have any force or even a roller is going to have any force of sufficient magnitude that's perpendicular to the surface, because it can roll. Same idea here. It can, if there's a force that gets developed in this direction, then it's going to roll. There is no friction. It's going to roll. Yeah, I mean, it could slide, but I mean, yeah, so maybe this slides, but you're assuming this is operating like it's supposed to operate. This is going to rotate. Well, okay, the force, there's negligible friction force, so the force is going to be perpendicular to the surface. So you know the angle of the force because you know it's perpendicular to the surface. But this is or because it could potentially be in both directions. The force could be either in this direction or this direction, because this can stop movement in either direction. Here, this is similar to the roller here, but because there's a pin here, there is no moment. But if we look here, there's no pin, so this can prevent rotation as well. So there's a moment here. Now, I'm not sure why they don't put an or here or a force in the other direction, right? Or but the goal here is just to give you an idea of the types of supports and the motion that they're preventing. So like here, we've got these two ors. Well, you're not going to know that might be an unknown. What the sense of the force is going to be an unknown. The theta is the same no matter what, but whether the force is this direction or this direction, you're not going to know. It's going to be dependent on all of the other forces in the free body diagram. It's just saying that, like how we talked about how there's some components like a pin connection where it's not designed to support like a force or a rotation in the 3D direction. This is saying, what this is saying is that this is designed to support. It can support a force. It's designed to prevent rotation or movement, translation in this direction or this direction. That's what it's saying. So this type of support is designed to support either one of these loads, but it has a pin here, so there's no rotation it's preventing. Here, this obviously can't prevent rotation. Here, even if this wasn't pinned, it couldn't stop rotation because of the roller or because of the rocker, okay? Here, obviously can't prevent rotation. How is these rollers going to prevent any rotation? Here, the link and the strings it's kind of like pin connections, so there's no rotation prevented. Here, pin connection, no rotation prevented. If we come here, here's a pin connection. You can represent it like we talked about. You can represent it with just two component forces or a force and an angle. Here, this can prevent rotation, and it's designed to prevent rotation as well. If you want to have something set up to where you want to prevent translation in this direction and rotation in this direction, this kind of link could work. And then fixed support prevents all types of motion, all rotations and all translations, at least in the plane. All right, here's some typical examples of actual supports that you see in the real world. When you're driving around, take a look. You'll notice some of these. Here's a cable force connected with a pin. So that's, if we come to this cable here, you can think about that like a pin. It could be just tied in here, but it's still like we see here. It's a cable or a string is like a pin connection. Here's an example where there is actually a pin connecting a cable here. The cable exerts a force on the bracket in the direction of the cable. Here's a rocker. The rocker support for the bridge girder. Yeah, you can see these types of supports take a look at like when you're going over a bridge. And if you can sometimes see the supports on the bridge, you'll see these. These allows horizontal movement so the bridge is free to expand and contract due to a change in temperature. Here's this concrete girder rests on the ledge that is assumed to act as a smooth contacting surface. Right, here's like a smooth contact. It prevents motion in this direction, but I'm assuming it's a similar idea here. If the temperature changes, this can expand and contract and it can move a little bit. It can expand or contract in this direction. But it's constrained at the other end to where there's no way it could slide off. That's not possible, but it can still expand and contract from temperature. Or even just like vibrations or whatever. If it's fixed, you could have these unnecessary stresses. Okay, here's a pin support. And then here's these beams are welded here. These are fixed supports, welded. They're welded. All right, internal forces. I go into detail on internal forces in the full-length free body diagram video. Again, the link is posted in the description. We don't consider internal forces in free body diagrams, only forces on exposed surfaces. For all the exposed surfaces in the free body diagram, if there's contact at those exposed surfaces between something from the environment that we took that body from, then that's where forces are going to be. And then there's also non-contact forces, weight. So they talk about weight and center of gravity. We talked about this. All right, idealized models. Let's read through this section. When an engineer performs a force analysis of any object, he or she considers a corresponding analytical or idealized model that gives results that approximate as closely as possible the actual situation. That's an important part of being an engineer. You're trying to simplify whatever problem you're trying to solve as much as you possibly can without compromising I don't want to say quality, because quality is relative to the design goals. So you simplify the problem as much as you can without compromising the design goals, the quality goals. You don't want to have any unnecessary complications, unnecessary costs. You don't want to make something cost too much, or you don't want to make something that's possible to solve seem like it's impossible to solve. To do this, careful choices have to be made so that selection of the type of supports, the material behavior, and the object's dimensions can be justified. This way, one can feel confident that any design or analysis will yield results which can be trusted. In complex cases, this process may require developing several different models of the object that must be analyzed. In any case, this selection process requires both skill and experience. The following two cases illustrate what is required to develop a proper model. In figure 5.5a, so this here, the steel beam is to be used to support the 3 roof joists of a building. For a force analysis, it is reasonable to assume the material, steel, is rigid since only very small deflections will occur when the beam is loaded. Yeah, so the rigid body assumption is a classic example of you would be a terrible engineer if you didn't use the rigid body assumption for pretty much anything we learn in this course. Because what you would get from solving a problem and not using the rigid body assumption, so actually accounting for the deflecting loads, what you would get out of that, the additional accuracy you would get would be so negligible, but you'd spend so much extra time, unnecessary time. So the reward you get it's like doesn't mean anything, and the time you put in is so much more. That's bad engineering. A bolted connection at A will allow for any slight rotation that occurs here when the load is applied, and so a pin can be considered for this support. At B, a roller can be considered since this support offers no resistance to horizontal movement. Building code is used to specify the roof loading A so that the joint loads F can be calculated. So these forces here, you might say, well, what load do I put here? The weight of these beams? No, you need to put the actual design loads. That's where these roofing codes will help give you the necessary loads you have to design for, or building codes. These forces will be larger than any actual loading on the beam, since they account for extreme loading cases and for dynamic or vibrational effects. Finally, the weight of the beam is generally neglected when it is small compared to the load the beam supports. The idealized model of the beam is therefore shown with average dimensions A, B, C, and D. So you neglect the weight of the beam, but maybe you could include the weight of the beam. Maybe it's not that big of a deal to include it, so just include it. It just depends. But one thing to think about is that I can't see what kind of support they're actually putting here, but you can still use for your model, you can, if let's say here, there's some weird exotic type of support, but the support is designed to prevent translation. Assuming this is a planar problem, it's designed to prevent translation, but not rotation. Well, you can just still model it with a pin, right? Like here, it looks like what they're doing is maybe it's got some sort of like geometrical connection here that prevents translation. This is not designed for anything into or out of the page. It's just preventing, obviously, it can't move down, so it's got a force there. And let's say it also prevents, it's locked in place to where it can't move left or right either. But it's got a space here. If there was no space here, if this was tight, it would be a fixed support. But since there's a space there, you can imagine if there's large loads, I'm going to exaggerate the deflection of the beam. Because there's a space there, this face can rotate. So there's no moment's going to develop. Well, that's not actually a pin, right? That's not a pin connection, but you can just model it that way. It is a pin. It's like a pin because it prevents translation but no rotation. So you just put a pin. And here, there's no actual roller there, but you're neglecting friction. I mean, I'm sure it's going to have to be locked into place somehow, but let's say it's only locked into place to where it can't move up or down, but it's like a loose connection. It's like a loose kind of geometrical, like the beam goes into a slot, like a cutout slot here, but it's loose, so it only supports vertical. It doesn't allow the beam to obviously go up or down here. But there is friction, but again, the friction, you don't consider friction for these enormous loads coming here. Friction is negligible, but that's okay. It's just preventing translation in a single direction, of only in certain directions relative to all the possible directions that it could be prevented. Well, you just put that as a roller. There's no actual roller here, but you put a roller for the model. See? All right. As a second case, consider the lift boom in figure 5.6a. Here, by inspection, it is supported by a pin at A and by the hydraulic cylinder CB or BC, which can be approximated as a weightless link. All right, so what they're saying is you're really looking at this entire beam and cage here. That's what you're looking at. That's what you're doing the free body diagram of. And if you're looking at this entire system, this hydraulic cylinder the weight is so small compared to this entire beam bucket here, whatever you want to call this. It's like a weightless link. And even these pin connection pieces here, these clevises, that's negligible. It's just all you're looking at is the weight of all of this combined. But again, I mean, look, if you know the weight of the cylinder, and if it's very easy to know the weight of these clevises in addition to the cylinder, well, then just go ahead and use that as the full weight. They're just trying to illustrate the kind of the mindset behind making assumptions. If it would be really complicated to find the center of gravity if you include this, well, maybe you can just neglect it. If you include the weight of the cylinder, well, then just neglect it. If it's not that big of a deal, then include it. All right, the material can be assumed rigid, and with its density known, the weight of the boom and the location of its center of gravity are determined. Here's the center of gravity. When a design loading P is specified, the idealized model shown in figure 5.6b can be used for a force analysis. Average dimensions are used to specify the location of the loads and the supports. So what they're showing is a nice idealized model of this setup is shown here. It's not the base of this is not actually fixed to the ground, but it's fixed to the machine. But that machine is like a rigid ground. You can think about it. The machine, the base here, that machine is not moving relative to all this. You can model it kind of like this. It's like this fixed, rigid base, and you got all this going on above it. Okay. Equations of equilibrium. In section 5.1, we developed the two equations which are both necessary and sufficient for the equilibrium of a rigid body, namely the sum of the forces is equal to 0 and the sum of the moments about any point you want are equal to 0. Right? That was the basic conditions for equilibrium of a general rigid body in 3D. When the body is subjected to a system of forces which all lie in the XY plane or a single plane, that's what we're going to focus on here now. In this section, we'll do 3D in another video, then the forces can be resolved into their X and Y components. Consequently, the conditions for equilibrium in 2 dimensions are, so what they're saying is, we're going to look at these from the standpoint of components in the Cartesian coordinate system. You could think about this for any kind of coordinate system, cylindrical, whatever, but we're going to think about the conditions for equilibrium. The sum of the forces are equal to 0, and the sum of the moments, the sum of all of the forces as of vectors, and the sum of the moments as about a point, these are vector sums, are equal to 0. We're going to break them down to components in the coordinate system. And we're just going to do that for 2D here. Now, I want to point out that, I want to point out 2 things. First of all, you might be wondering, well, where's Newton's laws here? And I'm not sure why they haven't mentioned it, but they might mention it later, but Newton's laws are coming into play because what is Newton's laws? Or what is Newton's second law? So it's force is equal to ma, and then there's also the idea of, from a rotation standpoint, torque, that's like moment, is equal to I alpha. This is angular acceleration. And I is like an equivalent, for a rotation standpoint, equivalent of mass. And again, torque is like moments. Well, for equilibrium, the linear acceleration is 0 and the angular acceleration is 0. So what happens is, the idea is the sum of the forces, and if you're thinking about this like just the general vector sum, like we started this section with, this chapter with, the sum of the forces, like if you simplify everything down to an equivalent force at a point, that force is going to be 0. If it wasn't 0, then you'd have a mass times acceleration to deal with. The sum of the moments is going to be equal to 0 as well. That equivalent couple moment is going to be equal to 0 as well. If it wasn't, you'd have an angular acceleration to deal with. You can think about this as having like an ma here, but a is equal to 0. This is like having an I alpha here, but alpha is equal to 0. Okay, and also I forgot to talk about the equilibrium of a particle. What was that about? Let's make sure we remember what this was about. The equilibrium of a particle was a special case where the entire force system on the free body diagram, the lines of action of all of the forces met at a point, and this could be in 2D or 3D. The lines of action of all the force acting on the body. You're doing all this starts with a free body diagram, right? You have a free body diagram, you've represented all the forces, and then you discover the lines of action of all of these forces meet at a common point, and that can be in 2D or 3D. Well, in that case, there is no moment. The forces have no net moment. Because you might say, well, why? You could pick a certain point in space and find the moment of the forces. Well, no. Okay, here, remember this condition here, we could pick any point we want. So let's just pick that common point to make it easy. Well, there's no moment about that point. There you go. So all we were doing in chapter 3 was that since all the forces met at a point, you could make a free body diagram just as a particle, as a point in space. You bring all the forces to that point and sum the forces about that point. And it was equilibrium, so they had to be zero. That's what we were doing. Okay, but if you break this down into components in the Cartesian direction, then you can do this on an axis by axis basis. You can sum the forces in the x, they have to be equal to zero. Sum the forces in the y, they have to be equal to zero. And then sum the moments about that same point. But you remember when you're summing moments about a point, you could also break that down into axes as well. And this moment, though, is like we remember for planar problems, that's going to be moments about the z-axis, because for a planar problem, there's only moments with direction coming into or out of the page. So that's the idea. All right, so now this is the most common. If you're breaking it down into Cartesian components in 2 dimensions, this is the most common, but there are alternative ways you can do this equilibrium, apply the equilibrium principle. So alternative sets of equilibrium equations. Although those equations here are most often used for solving coplanar equilibrium problems, 2 alternative sets of 3 independent equilibrium equations may also be used. One is, so the sum of the forces in the x is equal to 0, and then you pick two points to sum moments about. Some of the moments about A is equal to 0, some of the moments about B is equal to 0. When using these equations, it is required that a line passing through points A and B is not parallel to the y-axis. So you can also think about this as you could do some of the forces in the y is equal to 0, and then some of the moments about 2 points. In that case, a line passing through the 2 points here, A and B, couldn't be parallel to the x-axis. But let's just focus on this. So the line passing through A and B can't be parallel to the y-axis. So if that's the case, they want to prove that this works. To prove that equation 5.3 provide the conditions for equilibrium, consider the free body diagram of the plate shown in figure 5.11a. So let's start here. Using the methods of section 4.7, all the forces in the free body diagram may be replaced by an equivalent resultant force acting at point A and a resultant couple moment acting at point A. So you get a resultant force, you do a vector sum on all these, you can put it at any point you want, we'll put it at point A, then sum the moments of all these forces about point A and put a couple moment there at point A. That's valid, right? Everything we've done is valid so far. And here's the point B we're going to use, and here's the point A we're going to use for the moments here. But we've just started by breaking this down or simplifying this to an equivalent force and couple moment at point A. Okay, now if the sum of the moments about point A is equal to 0 is satisfied, it is necessary that resultant couple moment is equal to 0. Okay. Furthermore, in order that the resultant force satisfies the sum of the forces in the x is equal to 0, it must have no component along the x-axis. And therefore, this FR, the resultant force, must be parallel to the y-axis. Okay, so they're just showing how this works. This is valid, right? Now, since the sum of the moments about A are equal to 0, well, this is 0. This can go away. And since this also is going to be true, then there can't be a component of the force in the x direction. So this is the case here. So the last thing we need to see is, okay, what's the conditions so where the sum of the moments about B is equal to 0 is true? Okay, if it is required that the sum of the moments about B is equal to 0, where B does not lie on the line of action of the resultant force, then the resultant force is equal to 0. So if the last condition is satisfied, the only thing is, like, this couldn't be point B. Because, yes, if this was point B, if you sum the moments of the resultant force about point B, that's equal to 0. However, the issue is we're trying to use this equation here to show that the resultant force is equal to 0. Okay, so let's come back to these equations of equilibrium. We simplify this to a single resultant force in couple moment. For this resultant force, you need two components, both components, the x and the y component, to be equal to 0 to get rid of the force, and then the couple moment to be equal to 0, you get rid of the couple moment. If we come to these equations here, so first, the sum of the x components of the resultant force are equal to 0, so you get rid of the x components. Also, the sum of the moments about point A are equal to 0, so you get rid of this couple moment. So you're left with this, but you still have this resultant force to set equal to 0, to show that's equal to 0. If this is point B, then yes, that is true. The sum of the moments about point B do equal 0, but the moment arm is also equal to 0. So what you have is, the idea is, so FR times the moment arm about point C is equal to 0, but the moment arm is equal to 0, so that doesn't necessarily mean, even though this could be satisfied, that doesn't necessarily mean that FR is equal to 0. So the moment arm can't be 0. Then you show that FR is equal to 0, and the three equations, or the equilibrium is satisfied in the plane. All right, and looking here, this is another way you can set up equations of equilibrium. You can sum moments about three separate points. In this case, it's necessary that points A, the 3 points, don't lie on the same line. All right, to prove that these equations, when satisfied, ensure equilibrium, consider again the free body diagram of figure 511b. All right, so we come here. Again, there's no problem going from a general force system in a plane like this to a force and couple moment at a point, even if there was a couple moment included in here too, as long as the direction of the couple moment was into or out of the page. Coming to simplifying that to a force and couple moment at this point A, that's no problem. And we're going to see parallels of all of this in 3D as well. If the sum of the moments about point A is equal to 0 is to be satisfied, then the resultant couple moment about point A is equal to 0. Okay, so the couple moment is satisfied. The sum of the moments about point C is equal to 0 is satisfied if the line of action of the resultant force passes through point C. And then finally, if we require the sum of the moments about point B is equal to 0, then means that it's necessary that the resultant force is equal to 0. And so we've shown that net resultant couple moment and resultant force are equal to 0, so the plate must be in equilibrium if these three equations are satisfied. Now, you might be a little confused here, because it seems as though perhaps this is redundant. The sum of the moments about point C is satisfied if the line of action of the resultant force passes through point C. Well, the idea is that we have no idea what the direction of the resultant force is. We're setting all of this up in complete general. We can't make any statement about the direction of this resultant force. We did here because of one of the equations of equilibrium. The x component of the resultant force is equal to 0, so we knew that the resultant force had to be in the y direction. For this case, with the sum of the three moments about three separate points, we can make no statement about the direction of the resultant force. So for the sum of the moments about point A is equal to 0 equation, this couple moment is gone. The sum of the moments about point C, we'll assuming that this point C is not on the same line as the line from A to B, that's a requirement. The points A, B, and C can't be on the same line. So since point C is somewhere off the line, it could be anywhere off this line, then just imagine there's going to be a component of the force in the direction of C. The sum of the moments about that point are going to be equal to 0. And what's remaining is not going to be along the line of action of B. It can't be, because C is not on this line, which gets rid of the force, which constrains the force to have to be equal to 0. And then one thing to point out too is that it wouldn't even be necessarily desirable to have just two equilibrium equations, because the more equations, then the more unknowns you can solve for. So I want to point that out as well. All right, so now let's work some example problems, and then we'll move on to section 5.4.